Hey guys, tonight on Slumber Expeditions, we journey back over 4.5 billion years to witness the single most violent day in our planet's history, the colossal impact that gave birth to our moon. We will stand on the surface of a hellish, molten Earth as it is struck by a Mars-sized planet named Theia, an event that vaporized continents and spun our world into a maelstrom of liquid rock. Our exploration will visualize this apocalyptic collision in unprecedented detail, from the initial, silent approach of Theia to the formation of a glowing ring of debris around our wounded planet. We will then follow the long, turbulent aftermath as this new, hybrid Earth began its slow cooling, transforming from a global ocean of magma into a world with the first solid crust and the first steaming, primordial oceans, setting the stage for all of life's future history. So before you settle in, if you're finding comfort in these deep time cataclysms, please consider liking this video and subscribing to the channel, but only if you genuinely like what we do here. We would also love to hear from you in the comments below. Tell us where you are listening from and what time it is there. It's always fascinating to connect with a global community of curious minds who share this fascination with our planet's greatest enigmas. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's speculative journey together. Let the silent, patient presence of the moon itself guide you back to the moment of its violent, beautiful birth. You are a consciousness adrift in the swirling, incandescent heart of the solar nebula 4.5 billion years ago. There is no up or down, only a dizzying, three-dimensional ballet of cosmic dust and gas, all spiraling relentlessly inward toward the furious, newborn sun at the center. You are not standing on anything, for there is no ground, only the searing heat of accretion and the constant, percussive flash of mountain-sized planetesimals colliding and merging all around you. Each impact a silent, brilliant firework in the vacuum, building worlds from chaos. This is the construction zone of the solar system, a violent, beautiful, and terrifying nursery where the Earth and its sibling planets are being forged in a continuous, shattering roar of creation and destruction. This era, known to us as the Age of Planetary Accretion, was a time of continuous, shattering violence on a scale that defies imagination. The early solar system was a cosmic shooting gallery, with countless planetesimals on intersecting, chaotic orbits. Collisions were not rare, catastrophic exceptions. They were the primary and essential mechanism of growth. When two planetesimals met, they could merge, creating a larger, more massive body, but these mergers were never gentle. They were titanic impacts, releasing energies so vast they would make the combined force of all humanity's nuclear arsenals seem insignificant. Each monumental impact would instantly melt the colliding bodies, forming vast, transient magma oceans on their surfaces and homogenizing their interiors through the sheer force of the impact. It was through this brutal, chaotic process of collisional growth, a form of planetary cannibalism, that the terrestrial planets, Mercury, Venus, Earth, and Mars, were painstakingly forged. They were not born whole and complete, but were assembled piece by piece in a cosmic foundry of immense heat and pressure, their very atoms fused together in the heart of countless collisions that define the first 100 million years of the solar system's life. Amidst this relentless chaos, our own proto-Earth was steadily growing, gravitationally sweeping up material from its orbital path like a cosmic snowball rolling through a blizzard of rock and metal. It was a world without a defined, solid surface as we know it. Its interior was a seething, molten mass, a churning cauldron of liquid rock heated by three powerful and relentless sources. The first was the immense energy released from the radioactive decay of short-lived isotopes like aluminum, 26 elements forged in a long-dead star and incorporated into the planet's building blocks. The second was the gravitational potential energy converted to blistering heat as the planet accreted more mass and compressed under its own ever-increasing weight. The third was the residual heat from the countless giant impacts it was continuously suffering, each one delivering a fresh pulse of thermal energy into its deep interior. There was no solid crust to speak of. The entire planet was likely a global ocean of magma, a sphere of liquid rock thousands of kilometers deep, glowing with a fierce, hellish incandescence that would have been visible from space. The sky above this molten world would have been a perpetual, glowing orange, illuminated not by a sun as we see it, but by the constant glare of the molten surface itself and the frequent, brilliant flashes of incoming planetesimals vaporizing in the thick, primitive atmosphere that clung to the young planet. This primordial atmosphere was a thick, suffocating blanket of gases that had been outgassed from the churning molten interior or delivered by the icy comets and water-rich asteroids that were still pummeling the young world. It was a toxic, reducing brew of water vapor, carbon dioxide, nitrogen, hydrogen, methane, and ammonia, with not a single molecule of free oxygen to be found. The pressure at the surface would have been immense, hundreds of times greater than it is today, creating a crushing, superheated environment. There were no oceans of liquid water, for the surface temperature was far above the boiling point of water at any pressure. Any water that existed was locked in the atmosphere as superheated steam or dissolved within the molten rock of the magma ocean itself. This was the Hadean Aeon in its truest sense, a world named for Hades, the Greek god of the underworld, a planet that was the very definition of a hellscape, a crucible of fire and rock where the most foundational events in our planet's history were about to unfold in a final, definitive act of creation through destruction. It was into this violent, formative context that a final, defining player entered the stage, a Mars-sized protoplanet that scientists have named Theia. Theia, named after the mythical Greek Titan who is the mother of Selene, the moon goddess, was a world in its own right, perhaps one-third the mass of the proto-Earth, a substantial planetary embryo. It is theorized that Theia had formed in a stable orbital resonance with the proto-Earth, likely at a Lagrange point, peacefully sharing the proto-Earth's orbit around the Sun for millions of years. But the gravitational tugs from other growing planets, particularly the burgeoning giant Jupiter, would have acted like a gravitational pest, slowly and inexorably destabilizing this delicate balance. Over millions of years, Theia's orbit became increasingly erratic, its path around the Sun beginning to intersect with that of the proto-Earth in a fateful convergence. A collision became not just a possibility, but a mathematical and dynamical inevitability. The stage was set for the single most important event in Earth's early history, an impact so colossal it would wipe the planetary slate almost clean and create a whole new world from the ashes of the old, a world destined to be accompanied by a loyal companion that would forever grace its night sky and stabilize its very spin. The moment of impact arrived not with a warning, but with the silent, inevitable certainty of celestial mechanics. Theia, a planetary body with a diameter of perhaps 6,000 kilometers, closed in on the proto-Earth at a velocity of over 10 kilometers per second, on a trajectory that was not a glancing blow, but a direct, head-on collision. The angle is likely oblique, around 45 degrees, a factor that would prove crucial for the outcome, ensuring a more thorough mixing of the two bodies and launching a sufficient mass of material into orbit. From the surface of the proto-Earth, if any stable vantage point could have existed in the molten chaos, the approach would have been a terrifying spectacle of cosmic proportions. Theia would have grown from a bright, menacing star into a second, dull red sun, its glow swelling to fill an ever-increasing portion of the sky, its gravitational pull already beginning to exert a monstrous influence, raising colossal tides of magma hundreds of kilometers high across the globe and stretching the very planet into a slight, pre-impact egg shape. The final moments would have been a silent, horrifying crescendo before the sound, the heat, and the light of Armageddon arrived, a silence born in the vacuum of space, soon to be filled with the energy of a reborn world. The actual impact is almost beyond the scope of human comprehension, an event of such raw, transformative power that it defines the boundary of planetary scale violence. When Theia struck, it did not simply crash into the proto-Earth, it merged with it in an event of total, apocalyptic violence that lasted for several hours. The kinetic energy of the collision was staggering, equivalent to trillions of our most powerful thermonuclear bombs detonating at once. In the first microseconds, Theia's dense iron core, along with a significant portion of the proto-Earth's own mantle, was compressed, heated, and utterly obliterated into a state of superheated plasma. The shockwave propagated through both bodies at hypersonic speeds, not as a wave of sound, but as a wave of instantaneous vaporization. The immense energy release instantly turned a large fraction of both planets into a superheated, incandescent cloud of vaporized rock and metal, with temperatures soaring to tens of thousands of degrees Celsius, hotter than the surface of the sun. Theia was completely destroyed as a coherent body, and the proto-Earth lost a significant part of its own substance in this fiery exchange. The two worlds ceased to be distinct entities, their materials, their mantles and cores, violently mixed and flung into space in a cataclysmic, incandescent spray of debris that expanded rapidly from the point of impact. From this expanding, toroidal cloud of vaporized rock and molten droplets, a new, temporary structure began to form around the wounded, reeling Earth, a vast torus, or a disk, of incandescent material. This was the protolunar disk, a swirling, donut-shaped ring of debris that orbited the battered planet, extending out to a distance of several Earth radii. The disk was not a calm, Saturn-like ring of ice and dust. It was a turbulent, seething maelstrom, glowing with the intense heat of its own formation, its temperature so high that even the hardest rocks were in a gaseous or superheated liquid state. Within this disk, the familiar physics of accretion began anew, but on a vastly accelerated and frantic timescale. The vaporized silicate material began to condense into trillions upon trillions of molten droplets as it radiated its heat into space. These droplets collided and coalesced, first forming countless small moonlets, and then, through a process of runaway accretion, these moonlets rapidly merged over a period of perhaps only a few decades to a century to form a single, dominant body. In a remarkably short period of time, geologically speaking, the majority of the debris in the disk had coalesced to form the protomoon. It was born not in the cold, peaceful void of space, but in the fiery, chaotic embrace of its parent planet, a child of unimaginable catastrophe, its birth witnessed only by the scarred Earth itself. The immediate aftermath of the impact left the Earth transformed into a world more alien and terrifying than any in our modern solar system. The planet had been superheated by the sheer energy of the impact, its entire surface, and a substantial portion of its mantle down to a depth of 1,000 kilometers or more, melted once again into a deep, global magma ocean, far more extensive and hotter than any that had existed before. This was not a mere surface feature, it was a planetary scale phenomenon, a sea of liquid rock so deep it could have swallowed mountains whole. The heat was so intense that a significant portion of the Earth's rocky mantle was vaporized, creating a temporary, incredibly dense atmosphere of vaporized rock, silicate vapor, that would have exerted a surface pressure thousands of times greater than our present atmosphere. The sky would have been an opaque, glowing fog of rock vapor, glowing with a dull, pervasive red heat that outshone the sun, which would have been completely obscured as a dim, fuzzy disk in the perpetual, incandescent twilight that enveloped the planet. This was a world in the throes of a fever, its very rock having been boiled into the sky. The newly formed moon, meanwhile, was incredibly close to the Earth, perhaps only 20,000 to 30,000 kilometers away, compared to the 384,000 kilometers of today, while inside the geostationary orbit of the modern era. In the sky, it would have appeared as a colossal, terrifying presence, a burning red orb 20 times larger than the modern full moon, its surface still a churning magma ocean, dominating the heavens and casting a baleful, hot light upon the Earth below. The Earth day was drastically shorter, spinning on its axis in just a few hours due to the immense angular momentum transferred from the oblique impact. The gravitational interactions between the Earth and its new, massive companion were ferocious and immediate. The tides raised in the Earth's magma ocean would have been thousands of meters high, creating a perpetual, global sloshing of the planet's molten surface, a rhythmic pulsing that added to the geologic chaos. This was the scene in the hours, days, and years following the impact, a twin-world system of two glowing, molten spheres locked in a violent, intimate gravitational dance, a binary planet system born from utter destruction and poised on the uncertain edge of a long, slow cooling process that would eventually, over hundreds of millions of years, give rise to the stable, life-bearing planet we call home. The furious, incandescent heat that suffused the entire Earth-Moon system following the Theia impact could not last forever. This immense thermal energy, though vast on a planetary scale, was a finite resource, bleeding relentlessly into the cold vacuum of space through the process of radiation. The global magma ocean that covered the Earth, though thousands of kilometers deep, thus began its long, stately process of solidification, a pivotal chapter that would determine the very internal structure and geochemical destiny of our world for billions of years to come. This cooling was not a simple, uniform process like the skin that forms on a pot of cooling lava. It was a complex, planetary-scale differentiation event governed by the principles of mineralogy and physics under extreme conditions. The cooling did not happen from the top down as one might expect. Instead, the deepest parts of the magma ocean, under the immense pressure of the overlying rock, likely began to crystallize first. Dense minerals like magnesium-rich olivine and pyroxene, which have the highest melting points, were the first to solidify into microscopic crystals. Being denser than the surrounding melt, these crystals then sank like a slow-motion snowstorm, forming the earliest seeds of what would become the Earth's solid lower mantle. This process, known as fractional crystallization, began to chemically separate the Earth, creating distinct layers of different composition and density, and setting the stage for the future chemical evolution of the planet. As the mantle slowly solidified from the bottom up, a crucial buoyant separation was occurring that would ultimately create the continents we walk on today. Certain elements, known as incompatible elements, did not fit easily into the tight, orderly crystal structures of the common mantle minerals like olivine and pyroxene. These included large ion lithophile elements like potassium, uranium, and thorium, which are also radioactive, as well as elements that favored forming networks of silicon and oxygen, like silica and aluminum. These elements were progressively concentrated in the remaining liquid magma as the mantle crystals settled out. This residual melt became increasingly enriched, a geochemical soup that was less dense than the solidifying mantle beneath it. This buoyant, enriched magma, the dregs of the crystallization process, would slowly percolate and migrate upwards over millions of years, eventually pooling at the very top of the solidifying mantle. Over tens of millions of years, this process created the first permanent crust of the Earth, a thin, global, and likely discontinuous shell of lightweight, granitic rock, known to geologists as the primary crust. This was not the familiar, thick continental crust of today, but a primordial, basaltic to granitic skin that was destined for a short, violent life, continuously recycled by relentless impacts and the intense internal heat of the young planet. No definitive sample of this primary crust is believed to survive on Earth today, having been long since seducted back into the mantle or buried and remelted under eons of subsequent geological activity. While the rocks were slowly solidifying from the bottom up, the atmosphere was undergoing its own dramatic and transformative journey. The initial post-impact atmosphere of vaporized rock, the silicate vapor, was incredibly short-lived in geological terms. As the Earth's surface temperature plummeted below the condensation point of rock-forming minerals, around 2,500 degrees Celsius, the silicate vapor would have rained out over a period of perhaps 1,000 years. This was not a rain of water, but a rain of liquid rock droplets, a literal, global shower of molten rock and mineral condensates falling from the sky onto a surface that was itself still largely molten. It was a surreal precipitation event that helped to cool the atmosphere and add to the crystallizing surface. Once this rock vapor had condensed and fallen, the underlying primitive atmosphere, which had been outgassed from the churning magma ocean during its cooling, was revealed. This atmosphere was a thick, dense, and toxic blanket of gases, predominantly water vapor, carbon dioxide, nitrogen, and traces of methane, ammonia, and hydrogen sulfide. The surface pressure was still immense, and the surface temperature, while falling, was still many hundreds of degrees Celsius, far too hot for liquid water to exist in any stable form. Then came one of the most pivotal and dramatic moments in Earth's entire history, the condensation of the first permanent oceans, an event that began with the first true rain. As the surface temperature continued its relentless drop, it eventually crossed the critical threshold of 374 degrees Celsius, the critical point for water. Below this temperature, the superheated steam that made up the bulk of the atmosphere could no longer remain a gas, regardless of the immense pressure. It began to condense. The first rains would not have been gentle drizzles. They would have been a global, catastrophic deluge of superheated water, falling from a sky that was still scorchingly hot. These first raindrops would have sizzled and flashed back into steam upon hitting the hot rock below, cooling the surface in a violent, global feedback loop of evaporative cooling. For centuries, perhaps even millennia, this cycle continued, torrential rain falling, instantly flashing to steam, and rising again to form new clouds, slowly but surely sapping the thermal energy from the crust. Eventually, the surface cooled enough for the water to persist. The first permanent oceans began to form, initially as shallow, incredibly hot, and acidic bodies of water, pooling in the low-lying areas of the young, battered, and heavily cratered crust. The Earth, for the first time in its history, had stable liquid water on its surface, the single most important prerequisite and ingredient for the emergence of life. Throughout this entire multi-million-year period of cooling, crustal formation, and ocean condensation, the moon was a constant, looming, and dynamic presence in the sky. Its gravitational pull, from its initial close proximity, exerted a powerful and transformative influence on the young Earth. The Earth's day was still very short, perhaps only 5 or 6 hours long, resulting in a planet spinning with a ferocious rotational energy. This rapid spin, combined with the Moon's strong tidal force, created immense stress and frictional heating within the young, thin, and fragile crust and the still viscous mantle beneath. This tidal kneading likely drove intense and widespread volcanic and tectonic activity, helping to release more volatiles and gases from the planetary interior to replenish and modify the early atmosphere, and contributing to the rapid recycling and overturning of the earliest crust. The Moon itself was also cooling rapidly, its own smaller magma ocean solidifying to form the ancient crater highlands, or terrae, that we can still see today as the bright areas on its surface. The Earth-Moon system was slowly, laboriously settling into a new equilibrium, the raw, explosive violence of its birth giving way to the slower, more persistent and intricate geological rhythms that would, over the next several 100 million years, quietly set the stage for the most miraculous and profound event of all, the spontaneous emergence of the first self-replicating living organisms in a warm, chemically rich, and sheltered waters of the young planet's first oceans. As we conclude this part of our journey into the birth of the Earth and Moon, we'd like to extend a special thank you for listening. If you're finding comfort in these geological explorations, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It's always fascinating to connect with our global community of curious minds. You can also share which part of the story has captivated you the most so far. It would be wonderful to start a conversation around it. Now, let the mystery of what we've uncovered so far settle in your mind as we prepare to continue our exploration. The Earth, now swaddled in its first true oceans and a newly dense atmosphere, entered a phase of its existence that was no less dynamic than the fiery chaos of its birth, but one where the forces of change began to operate on a grander, more patient timescale. The sky above these steaming, primordial seas was a perpetual, leaden canopy, thick with water vapor, carbon dioxide, and nitrogen, a haze that diffused the sunlight into a dull, omnipresent glow. There was no blue sky to speak of. The high concentration of gases and the constant outgassing from a still violently active volcanic world scoured by relentless asteroid impacts scattered the sunlight in such a way that the heavens would have appeared a murky, orange-gray, a perpetual twilight even at midday. The sun itself, a key player in this drama, was a paradox. In its stellar youth, it burned about 30% less brightly than it does today, a celestial body still settling into the sustained nuclear fusion that would define its middle age. This faint young sun presents one of the great enigmas of early Earth science, for under its weaker light, a planet like modern Earth would have been a global, frozen snowball. Yet, the geological evidence written in the most ancient rocks tells a story of liquid water, of rivers and waves, of a world that was not only warm but likely hotter than our own in many periods. This apparent contradiction, known as the faint young sun paradox, finds its resolution in the very nature of that thick, primordial atmosphere that hung over the planet, a blanket so effective at trapping heat that it created a supercharged greenhouse effect, turning the entire world into a natural, planetary-scale hothouse. This early atmosphere was a chemical factory of immense complexity and activity, a realm where the raw ingredients of the planet were continuously churned and exposed to immense energies. Lightning, far more frequent and powerful than anything witnessed today, crackled through the ash-laden clouds above volcanoes and within the towering thunderheads that fed the endless rains. The relentless ultraviolet radiation from the sun, unfiltered by any protective ozone layer, beat down upon this chemical soup with untempered fury, breaking apart molecules and driving reactions that would be impossible in our modern, oxygen-rich air. Volcanic outgassing provided a constant supply of new reagents: water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, methane, and ammonia, while the impacts of comets and asteroids, which were still frequent occurrences in the inner solar system for hundreds of millions of years after the moon-forming impact, delivered not only water but also complex organic compounds, the so-called stuff of life. In this energetic, chaotic environment, the first prebiotic molecules began to form. Simple compounds like formaldehyde and hydrogen cyanide, which may sound toxic to us, were the essential building blocks, the alphabets in the primordial lexicon. Through a process of continuous synthesis, breakdown, and resynthesis in the oceans, the tidal pools, and even within the pores of hot rocks on the seafloor, these molecules began to link up, forming more complex chains like amino acids and nucleotides, the very monomers that would one day assemble into proteins and the informational code of life itself. The oceans were slowly becoming a dilute soup of organic material, a planetary-scale laboratory running a billion experiments at once. The surface of the Earth during this period, known as the Hadean and into the early Archean Eon, was a world of stark and dramatic contrasts, a landscape that would be utterly alien to our modern senses. The first solid crust, that thin, granitic skin formed from the dregs of the magma ocean, was not a stable, permanent platform. It was a fragile and transient membrane on a planet still bursting with internal heat. The tectonic regime was not the orderly, plate-driven process we see today, but something more chaotic and vigorous, perhaps a form of stagnant lid, tectonics punctuated by catastrophic overturns, or an early, more frenetic version of plate tectonics. The result was a crust that was continuously being recycled, broken apart by massive mantle plumes, and subsumed back into the hot interior. Volcanism was not localized to plate boundaries, but was global and rampant. The land, what little of it existed above the waves of the global ocean, was a black, basaltic landscape, jagged and sharp, composed largely of rapidly cooled lava flows with little soil to soften its contours. These first proto-continents, called cratons, were small, isolated islands scattered across a vast global ocean, their surfaces constantly resurfaced by lava flows and pockmarked by the scars of asteroid impacts. The soundscape would have been a relentless roar, the crash of waves on barren rock, the deep, subterranean rumble of the planet's unrest, the explosive decompression of volcanic eruptions, and the periodic, world-shattering sonic boom of a large asteroid or comet striking the ocean, sending tsunamis of superheated water thousands of feet high to scour the barren landscapes. The hydrological cycle, once established, began its relentless work of sculpting the planet. The rains, now falling on solid rock, began the slow process of erosion. Rivers carved their first channels down the steep slopes of volcanic peaks, carrying the first sediments, finely ground rock dust and volcanic ash, down to the sea, where they settled in thick layers on the ocean floor. These first sedimentary basins became the crucibles for further chemical complexity, layers of mineral-rich mud that could catalyze reactions and concentrate organic molecules. Hot springs and hydrothermal vents, both on land and deep on the ocean floor, played a particularly crucial role. These were not just sources of heat and minerals, they were natural electrochemical cells, with steep temperature and chemical gradients that could have provided the very energy source needed to drive the formation of complex organic molecules and perhaps even the first self-replicating systems. The entire planet was a system in a state of profound flux, a delicate and dynamic balance between the immense heat welling up from its interior, the energy pouring in from the sun, and the relentless cooling radiation into space. It was within this dynamic, often violent, but chemically rich and energy-rich environment that the conditions became just right, the parameters aligned, and the inert chemistry of the cosmos crossed a threshold into the realm of the living, setting in motion a chain of events that would, in time, utterly transform the planet for a second time, preparing it for a future it could not yet imagine. As the Earth's crust slowly solidified and its oceans deepened, its constant companion, the Moon, was engaged in a slow, stately dance of retreat, a gravitational ballet that would fundamentally shape the rhythms of the planet and create the stable environmental conditions necessary for the long, slow march of biological evolution. The mechanism driving this lunar recession was, and remains, the force of tides. The Moon's gravity does not pull uniformly on the Earth. It pulls more strongly on the side of the Earth closest to it, creating a gravitational bulge in the planet's flexible body, in its oceans, but also, significantly in this early period, in its solid but still semi-plastic mantle and thin crust. As the Earth rotates on its axis, this bulge is carried ahead of the direct line between the Earth and Moon. This offset bulge, in turn, exerts its own gravitational pull on the Moon, a subtle but constant tug that transfers rotational energy from the spinning Earth to the orbiting Moon. This energy transfer causes the Moon to slowly spiral outward, moving to a higher, slower orbit, while simultaneously acting as a brake on the Earth's rotation, gradually lengthening the day. In the immediate aftermath of the impact, when the Moon was a mere 20,000 kilometers away and the Earth day was a frantic 5 hours, this tidal braking was ferociously powerful. The rate of recession was likely several meters per year, a rapid retreat on geological timescales. As the Moon moved further away, its gravitational influence weakened, and the recession slowed to the more sedate pace of approximately 3.8 centimeters per year that we observe today. The consequences of this lengthening day and receding Moon were profound for the development of the Earth's environment and, ultimately, for life. The shorter, 5-hour day of the early Earth would have created a dramatically different climate system than the one we know. The frantic cycle of day and night would have meant that no part of the planet was exposed to sunlight or darkness for very long, leading to more uniform global temperatures, but also to weather patterns of unimaginable violence, with hurricanes and wind speeds that would make our most powerful modern storms seem like gentle breezes. As the day lengthened, these extremes began to moderate. The longer periods of sunlight allowed for greater heating of the surface, and the longer nights permitted more sustained cooling, establishing more pronounced temperature gradients between the equator and the poles, which in turn drove more stable and predictable atmospheric circulation patterns. The slowing of the Earth's rotation also had a crucial effect on the planet's magnetic field. The Earth's magnetic field is generated by the churning, convective motion of liquid iron in the outer core, a process known as the geodynamo. The rapid rotation of the early Earth would have influenced the flow patterns in this metallic ocean, and as the rotation slowed, the dynamics of the geodynamo subtly shifted, potentially helping to stabilize the field into the powerful, protective dipole shield it is today, a shield that was becoming increasingly vital. This magnetic field is one of the Earth's most unsung heroes, an invisible force field that defends the atmosphere and the surface from the relentless, sterilizing onslaught of the solar wind, a stream of charged particles ejected from the sun at supersonic speeds. Without a strong magnetic field, these particles would have gradually but inexorably stripped away the atmosphere, as is believed to have happened on Mars, which lost its global magnetic field early in its history and subsequently saw its thick atmosphere and surface water vanish into space. For Earth, the strengthening magnetic field acted as a deflector shield, channeling the solar wind around the planet and protecting the precious atmospheric envelope that maintained the greenhouse warmth and the pressure necessary for liquid water to persist. Furthermore, by deflecting these high-energy particles, the magnetic field also provided a crucial layer of protection for any fragile, early life forms that were beginning to emerge in the oceans, shielding them from mutation-inducing radiation and allowing chemistry to proceed with a degree of stability on the path toward biology. The Moon, through the very act of its retreat, was indirectly helping to fortify this planetary shield by moderating the Earth's spin. The gravitational influence of the Moon also played a direct and critical role in stabilizing the tilt of the Earth's rotational axis, and factor of paramount importance for long-term climate stability. The Earth's axis is currently tilted at about 23.5 degrees relative to the plane of its orbit around the Sun, a tilt which gives us our seasons. This obliquity is not fixed. It undergoes small oscillations over tens of thousands of years. However, without the Moon's stabilizing presence, the gravitational tugs from the other planets, particularly Jupiter, would induce wild and chaotic variations in the Earth's axial tilt, potentially causing it to wobble anywhere from 0 to 85 degrees over periods of a few million years. Such extreme variations would lead to climatic chaos, with the poles sometimes pointing directly at the Sun, boiling any ice and creating unimaginable weather patterns, while at other times the equator would be in perpetual twilight. This is the fate of Mars, whose small moons, Phobos and Deimos, are insufficient to stabilize its axis, which has wobbled between 15 and 35 degrees over its history, contributing to the dramatic shifts in its climate. The Moon, with its substantial mass and relative proximity, acts as a gravitational gyroscope, damping these extreme oscillations and confining the variation in Earth's axial tilt to a much narrower and more manageable range of only about 2.5 degrees. This stability has been a gift of immeasurable value, providing the consistent, predictable seasonal cycles that have allowed life to adapt and evolve over billions of years without being periodically wiped out by climate catastrophes induced by axial instability. The interplay between the receding Moon and the evolving Earth was thus a symbiotic relationship that crafted the very cradle of life. The lengthening days moderated the climate and weather. The tidal forces, though weakening, continue to drive the mixing of the oceans, preventing them from becoming stagnant and helping to circulate nutrients, while also contributing to internal geothermal heating through tidal friction, which in turn sustained volcanic activity and plate tectonics, the planet's long-term carbon cycle and temperature regulator. The stabilization of the axis provided the predictable environmental framework necessary for long-term evolutionary strategies. As the Moon continued its slow retreat, its apparent size in the Earth's sky shrank. A billion years after the impact, it would have been significantly closer than it is now, but no longer the terrifying, world-filling orb of the Hadean. It would have been a brilliant silver disk, still larger than today, casting a stronger, more silvery light on the nighttime landscapes of a world that was, by then, no longer barren and hellish, but one that was quietly, secretly, nurturing the first fragile sparks of life in the warm, dark depths of its global ocean. The stage was now set, the conditions perfected, the rhythms established. All that was needed was the spark and the patience of deep time to fan it into a flame that would eventually consume the world. The Hadean Eon, the first 500 million years of Earth's history following the planet's accretion and the Moon-forming impact, has long been considered a dark age, a period from which no tangible rock record survives, its history inferred solely from theoretical models and the evidence written in the Moon's own ancient face. The Earth's relentless geological engine, its plate tectonics and continuous crustal recycling, seem to have effectively erased all traces of this primordial epoch. For much of the history of geology, the Hadean was a true terra incognita, a blank page in the planet's biography. However, in recent decades, a remarkable detective story has unfolded, one that has begun to illuminate this dark age through the discovery of tiny, resilient time capsules, mineral grains that have survived the complete destruction of their parent rocks. The most important of these are zircon crystals, and their discovery has fundamentally rewritten our understanding of Earth's earliest chapters. Zircons, or zirconium silicate crystals, are extraordinarily durable, resistant to both physical weathering and chemical alteration. When they form in cooling magmas, they lock within their rigid crystalline structure not only the age of their formation, through the radioactive decay of uranium to lead, but also chemical clues about the environment in which they crystallized, offering us cryptic, yet profound, glimpses into the world of 4 billion years ago. The Jack Hills in Western Australia have proven to be the most prolific source of these Hadean time capsules. Here, within much younger sedimentary rocks that are about 3 billion years old, geologists have found detrital zircon crystals, zircons that were eroded from their original source rocks, transported by water and redeposited, that are vastly older than the rocks that now contain them. The oldest of these Jack Hill zircons have been dated to an astonishing 4.4 billion years, a mere 160 million years after the Earth itself formed and the Theia impact occurred. This date alone was revolutionary, proving that some form of solid crust existed much earlier than anyone had previously believed, a crust cool and stable enough to support the formation of granitic rocks, the parents of these zircon crystals. But the secrets of the zircons go far beyond their mere age. By analyzing the isotopic ratios of elements like oxygen and the trace amounts of other minerals included within them, scientists can perform a form of chemical paleontology. The oxygen isotope signatures in the oldest Jack Hill zircons suggest they formed from magmas that had interacted with liquid water. This single piece of evidence is staggering in its implication. It means that by 4.4 billion years ago, the Earth's surface had already cooled sufficiently for liquid water to exist, and likely for oceans to have begun forming, pushing back the timeline for the existence of the hydrosphere by hundreds of millions of years, and painting a picture of a Hadean Earth that was not a perpetually molten hellscape, but a world that may have had cool, solid crust and liquid water surprisingly soon after. Its cataclysmic birth. These zircon crystals also provide indirect evidence for the early establishment of plate tectonics, or at least some form of crustal recycling that could produce granitic rocks. Zircons with the chemical signatures of the Jack Hills crystals are typically formed in the kind of melting and differentiation processes that occur in subduction zones, where one plate slides beneath another. This suggests that some form of mobile lid tectonics, a process that recycles crust and creates new, differentiated continental material, may have been operating in some capacity as early as 4.4 billion years ago. This challenges the traditional view that the Earth was dominated by a single, stable, stagnant lid of crust for its first billion years. Furthermore, the hafnium isotope ratios in some of these ancient zircons tell another part of the story. The data suggests that the magmas from which they crystallized were derived from the remelting of an even older crust that had itself formed from a mantle that had been chemically differentiated very soon after the Earth's formation, likely during the crystallization of the magma ocean. This provides a tangible, material link to the very processes described in the cooling of the post-impact Earth, confirming that the large-scale chemical segregation of the planet happened with remarkable speed. The Hadean, as revealed by the zircons, was a period of dynamic and complex geology, with solid crust, liquid water, and likely some form of continent-building activity, a world that was, against all odds, already beginning to assemble the very foundations of a habitable planet. While the Earth's own Hadean record is fragmentary, we have a pristine, untouched archive from this period just a few days' travel away, the surface of the Moon. The Moon, being a much smaller body, lost its internal heat rapidly, and its geological activity largely ceased about 3 billion years ago, with only sporadic volcanism continuing until as recently as 1 billion years ago. This means its surface is a frozen museum, preserving a record of the earliest history of the inner solar system. The heavily cratered highlands of the Moon, its bright, mountainous regions, are composed of anorthosite, a rock that forms through the flotation of lightweight crystals in a magma ocean. These rocks, dating back to 4.4 to 4.5 billion years ago, are the direct evidence for the lunar magma ocean, the global ocean of molten rock that covered the Moon after its accretion from the debris of the Theia impact. By studying these rocks, brought back by the Apollo missions and identified by lunar orbiters, we have confirmed the magma ocean hypothesis for the Moon, which in turn strongly supports the same model for the early Earth. The cratering record on the Moon is our primary calendar for dating surfaces throughout the inner solar system. By counting the density of craters on a given lunar landscape, we can estimate its age. This record tells us that the Moon, and by extension the Earth, endured a period of intense bombardment for its first half-billion years, with a particularly violent spike known as the Late Heavy Bombardment around 4.1 to 3.8 billion years ago, a time when massive asteroids and comets scarred the face of both worlds. This lunar record provides the final, crucial piece of context for the environment of the early Earth. The Late Heavy Bombardment would have been a period of utter terror for the young planet. Impacts from asteroids dozens or even hundreds of kilometers in diameter would have been frequent enough to periodically sterilize the planet's surface, vaporizing the upper layers of the ocean and flash heating the atmosphere, potentially boiling the entire ocean away on more than one occasion. Any incipient life that had emerged in the earlier, more quiescent period revealed by the Jack Hill zircons would have faced an existential challenge. It either had to be incredibly resilient, perhaps finding refuge deep in the crust or at the protective depths of the ocean floor near hydrothermal vents, or it had to be capable of repeatedly re-evolving after each extinction-level impact. This paints a dramatic picture of the struggle for life's foothold, a planet that had provided the necessary ingredients and stable conditions surprisingly early, but which was then subjected to a cosmic pummeling that repeatedly threatened to wipe the slate clean. The fact that life not only emerged but persisted through this gauntlet of fire is a testament to its tenacity, and perhaps a clue that its origins are not in the sunlit surface waters, but in the sheltered, energy-rich, and impact-resistant depths of the subsurface and the deep-sea hydrothermal systems, where the planet's internal heat, not the sun, provided the sustaining energy, safe from the cataclysms that rocked the surface world above. As we conclude this part of our journey into the birth of the Earth and Moon, we'd like to extend a special thank you for listening. If you're finding comfort in these geological explorations, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It's always fascinating to connect with our global community of curious minds. You can also share which part of the story has captivated you the most so far. It would be wonderful to start a conversation around it. Now, let the mystery of what we've uncovered so far settle in your mind as we prepare to continue our exploration. In the profound, sunless depths of the early Archean oceans, far beneath the turbulence of impact-generated tsunamis and the violent churning of the surface waves, a quiet revolution was taking place. Here, In the eternal darkness, along the fissures of submarine volcanoes and within the porous, rocky crust of the seafloor, the final, momentous transition from complex chemistry to simple biology occurred. The most compelling hypothesis for the origin of life points to these hydrothermal vent systems, particularly alkaline hydrothermal vents like those found in the Lost City field in the mid-Atlantic. These structures are not belching black smoke of superheated water, but are graceful, carbonate chimneys that tower over the seafloor, percolating with warm, mineral-rich, alkaline fluids. They function as natural electrochemical reactors. This steep gradient between the alkaline fluid from the vent and the more acidic, metal-rich seawater creates a natural proton gradient across the microscopic mineral walls of the vent's porous structure, a gradient that is, in essence, the same fundamental power source that every living cell uses today to generate energy, stored in the molecule adenosine triphosphate, or ADP. Within the microscopic compartments and pores of these vent structures, the concentrated organic molecules from the primordial soup could have been sheltered, concentrated, and provided with a continuous, sustainable source of energy to drive their assembly into ever more complex structures, eventually leading to self-replicating RNA molecules and the first primitive cellular membranes that define the very first living entities. These first organisms, the last universal common ancestor, or LUCA, of all life on Earth, were not plants nor animals, nor even bacteria as we would easily recognize them. They were chemosynthetic, single-celled prokaryotes, drawing their energy not from the faint, young sun, but from the chemical disequilibrium of their environment. They likely consumed simple molecules like hydrogen, carbon dioxide, and sulfur compounds, metabolizing them to produce methane or acetate, in processes similar to those still used by modern archaea and bacteria found in similar extreme environments today. For these pioneers, the moon played an indirect but vital role as a planetary stabilizer. The stable axial tilt ensured that the climate, while hot and volatile, did not descend into the kind of chaotic extremes that would have periodically sterilized the entire planet. The gradually lengthening day provided a more moderate and predictable daily cycle, even in the deep ocean where sunlight did not penetrate, as it would have influenced surface currents and mixing patterns. Most importantly, the tidal forces, though weaker than in the Hadean, continued to flex the oceanic crust, helping to maintain the volcanic and hydrothermal activity that provided the energy and mineral nutrients for these early, vent-dependent ecosystems. Life was a tenuous flame, but the Earth-Moon system had crafted a deep, protected cradle in which it could not only flicker, but grow. For over 1 billion years, this chemosynthetic, anaerobic life was the pinnacle of biological complexity on Earth. The atmosphere remained devoid of free oxygen, a reducing atmosphere of nitrogen, carbon dioxide, water vapor, and methane. Then, around 2.4 to 2.3 billion years ago, a catastrophe of biology occurred that would dwarf any asteroid impact in its transformative power, the Great Oxidation Event. A group of microbes, the cyanobacteria, had evolved a miraculous and, for the existing world, a deeply destructive new metabolic pathway, photosynthesis. They had learned to harness the energy of sunlight to split water molecules, using the hydrogen to build sugars and releasing the oxygen as a waste product. For millions of years, this oxygen was quickly mopped up by the abundant dissolved iron in the oceans, precipitating out as vast layers of banded iron formations, the source of much of the world's iron ore today. But eventually, the sinks were saturated and oxygen began to accumulate in the atmosphere for the first time. This was a poison to the anaerobic life that had dominated the planet, causing a mass extinction on a global scale. Yet, from this crisis emerged opportunity. The rise of oxygen created the ozone layer, shielding the surface from harmful UV radiation and allowing life to eventually colonize the land. It also provided a much more efficient form of metabolism, aerobic respiration, which released far more energy from organic molecules than anaerobic processes. This energy windfall paved the way for the evolution of larger, more complex eukaryotic cells and, eventually, multicellular life. Throughout this long, slow biological saga, from Luca to the rise of eukaryotes, the Moon was a silent, constant witness, its gravitational influence woven into the very fabric of the planet's functioning. The tides it generated created a unique and challenging environment in the intertidal zones, areas that were periodically submerged and exposed. This rhythmic, predictable stress may have acted as a driver for evolutionary adaptation, encouraging resilience and the development of new survival strategies. The steady recession of the Moon continued to lengthen the day, providing a slowly changing parameter to which life had ample time to adapt. The stability of the climate, courtesy of the Moon's gravitational anchoring of the axial tilt, cannot be overstated. It provided the consistent environmental background against which the slow, patient algorithm of natural selection could operate, filtering and refining life forms across billions of generations. It is not an exaggeration to say that the predictable rhythms imposed by the Earth-Moon system, the day, the month, the tides, created the temporal framework within which life's circadian and circulunar biological clocks would evolve, internal rhythms that to this day govern the physiology and behavior of countless organisms. From the grunion fish that spawn on beaches with the high spring tides to the reproductive cycles of many marine creatures. The journey from a sterile, molten world to a planet teeming with life is the greatest story ever told, and the Moon is a central character in that narrative. Its birth and a violent impact set the initial conditions, creating a planet with a massive iron core, a rapid spin, and a composition that was a hybrid of two worlds. Its subsequent gravitational partnership provided the stability, the mixing, and the moderating influences that allowed the delicate, protracted processes of chemical and biological evolution to proceed without being constantly reset by cosmic or climatic disasters. The cradle of life was not just the warm little pond, but the entire planetary system, a system whose dynamics were and still are fundamentally shaped by its celestial companion. As life slowly diversified and complexified in the oceans, eventually setting its sights on the barren continents, it was stepping onto a stage that had been prepared over billions of years, a stage whose very stability was a gift from the cataclysm that had occurred in the deep past, a cataclysm whose silver mirror now hung in the sky, a constant reminder of a violent beginning that made a peaceful, living present possible. As complex life flourished in the oceans and eventually ventured onto the land, evolving through the ages of dinosaurs and the rise of mammals, the Moon continued its slow retreat, its face a constant in the ever-changing terrestrial biosphere. Its gravitational influence remained a tangible, physical force, shaping the coastlines with its tides and subtly influencing the life cycles of countless species. Then, very recently in geological time, a new species emerged, one that would look upon the Moon not just as a source of light or a trigger for instinctual behavior, but with a conscious, questioning wonder. For humanity, the Moon became more than a physical object. It became a central pillar in the architecture of our consciousness, our culture, and our earliest attempts to understand the cosmos and our place within it. The most immediate and undeniable influence of the Moon on human civilization was, and is, the tide. For prehistoric coastal communities, the rhythmic pulse of the ocean was as fundamental as the rising and setting of the sun. The tides dictated the best times for fishing, for harvesting shellfish, for launching boats, and they defined the very geography of the shoreline, creating a dynamic, intertidal world rich in resources. Understanding the patterns of the tides, which are a complex interplay of the lunar and solar gravitational pulls, was a matter of survival and economic necessity, making the moon an intimate and practical part of daily life. This practical relationship soon blossomed into a cultural and spiritual one. The moon's regular, predictable cycle of phases, from the dark new moon to the brilliant full moon and back again, provided humanity with its first and most natural calendar. This 29.5-day cycle, the synodic month, became the basis for timekeeping in countless ancient cultures, long before the solar year was precisely measured. The lunar calendar organized religious festivals, agricultural activities, and social rituals. The moon was a deity in nearly every pantheon, a powerful, changeable, and often feminine force. She was the Mesopotamian Sin, the Greek Selene, the Roman Luna, the Chinese Chama. She was a symbol of cyclicality, of birth, death, and rebirth, as she waned and waxed each month. She governed the concepts of time, fate, and the hidden, subconscious realms of the mind. Her association with the night made her a figure of mystery, intuition, and sometimes fear, but also of gentle guidance and reflective beauty. The silent, silver light of the full moon illuminated the nocturnal landscape, extending the day for travel, hunting, and social gathering, and casting the familiar world in an unfamiliar, dreamlike pallor that surely stirred the imagination and inspired the first myth-makers and storytellers. This deep, mythic connection evolved into a scientific one as human curiosity began to systematically observe and record the heavens. Ancient astronomers from Babylon, Greece, India, and China meticulously charted the moon's motion, its phases, and its occasional eclipses. They began to understand the intricate dance between the Earth, Moon, and Sunday. The Greek philosopher Anaxagoras, in the 5th century BCE, correctly reasoned that the moon shone by reflected sunlight and that lunar eclipses were caused by the Earth's shadow falling upon it. Aristarchus of Samos even attempted to calculate the distances to the sun and moon using geometric methods. The moon became a celestial laboratory, a testing ground for early scientific ideas about the nature of the cosmos. Its predictable behavior provided evidence for an ordered, comprehensible universe governed by mathematical laws, a concept that would lay the groundwork for the scientific revolution millennia later. The moon was the first foreign world, the first proof that the Earth was not the entirety of existence, and gazing upon its cratered surface inevitably led to the question of what it was, and whether it, too, could be a world like our own. This lineage of observation, wonder, and scientific inquiry culminated in the single greatest technological achievement of the 20th century, the Apollo program. When humans first set foot upon the lunar surface on July 20th, 1969, it was not merely a political or technological triumph, it was the fulfillment of a dream as old as humanity itself. The giant impact theory, which we have explored in such detail throughout this documentary, was itself a product of the Apollo era. The rocks brought back by the Apollo astronauts were the final, conclusive evidence that allowed scientists like William Hartmann and Donald Davis to propose their then radical hypothesis in 1975. The chemical fingerprints of those rocks, their similarity to Earth's mantle but with a telling depletion of volatile elements, were the ultimate clues that solved the 4.5 billion-year-old mystery of the moon's origin. The Apollo landings transformed the moon from a distant symbol, a face in the sky, into a tangible place, a physical world with a history intertwined with our own. The iconic photograph, Earthrise, taken from lunar orbit by the Apollo 8 crew, forever changed our perception of ourselves, showing our world as a fragile, beautiful and isolated blue marble hanging in the black void of space, a perspective that profoundly fueled the environmental movement and gave us a new sense of planetary identity and responsibility. The human connection to the moon, therefore, is a multi-layered tapestry woven from threads of practical necessity, mythological symbolism, scientific curiosity, and exploratory courage. It is a relationship that has evolved as we have evolved. We no longer worship the moon as a goddess, but we understand its gravitational influence with Newtonian precision. We no longer simply fear its eclipses as omens, but we predict them centuries in advance and use them to confirm the theories of relativity. Yet, despite our scientific mastery, the moon has lost none of its power to inspire awe. On a clear night, when we look up at its familiar, cratered face, we are connected to every human who has ever lived, to our ancestors who told the first stories about the rabbit in the moon or the man in the moon, to the ancient astronomers who first mapped its seas, and to the modern scientists who deciphered its violent birth. We are also, in that moment of contemplation, feeling the gentle, invisible pull of a gravity that has shaped our planet, our biology, and our history since the very beginning, a silent force that continues to guide the tides of our oceans and, perhaps, the tides of our imagination. As our journey draws to a close, we are left to contemplate the profound and perhaps unique relationship between our world and its satellite. The Earth and the Moon, when considered as a binary system, present a series of remarkable cosmic coincidences that have been essential in creating the conditions for a stable, long-lived, and complex biosphere. The most striking of these is their relative size. The Moon is just over 1/4 the diameter of Earth, and about 1/81 st of its mass. This makes it exceptionally large in proportion to its host planet, a ratio unmatched by any other planet-moon system in the solar system. Pluto and its largest moon Charon come close, but they are both small, icy bodies in the Kuiper Belt. For a terrestrial planet like Earth, our moon is a giant. This large size was a direct consequence of the specific nature of the Theia impact. The size of the impactor, the angle of the collision, and the velocity all had to fall within a fairly narrow range to result in a debris disk massive enough to form our moon, but not so violent as to completely shatter the proto-Earth. Had Theia been smaller or the impact more glancing, we might have no moon at all, or only a few small, captured asteroids like the moons of Mars. Had the impact been more direct or Theia larger, the result could have been the utter destruction of both bodies. We exist, with our large moon, in a sweet spot of cosmic violence. This specific configuration has had cascading consequences throughout Earth's history. The moon's large mass is the reason its tidal forces are so significant, driving the mixing of the early oceans and contributing to the internal geothermal heat that helps sustain plate tectonics. Its large mass is what allowed it to effectively act as a stabilizing gyroscope for the Earth's axial tilt, preventing the climate chaos that would otherwise have been induced by gravitational perturbations from Jupiter and Venus. The angular momentum transferred from the impact gave the Earth its rapid initial spin, and the subsequent transfer of that momentum to the Moon during its recession has given us a day length that is, in the present epoch, ideally suited for a temperate climate, balancing the heating and cooling cycles that drive our weather systems. It is a delicate and intricate chain of cause and effect, a cascade of contingencies that began with a single, random collision over 4 billion years ago. One is left to wonder how common such finely tuned events are in the cosmos. How many terrestrial planets undergo such a perfect impact that leaves them with a large, stabilizing moon, a robust magnetic field, plate tectonics, and a climate stable for billions of years? The answer to this question lies at the heart of the search for life beyond Earth. The moon's role is not only in the deep past or the biological present, it also points the way to humanity's future in space. Its surface, airless and geologically dormant, is a pristine archive of the solar system's history, a record largely erased on the geologically active Earth. It is a stepping stone, a natural space station from which to learn how to live and work on another world, with lower gravity and readily available resources like water ice trapped in permanently shadowed craters at its poles. The knowledge we gained from the Apollo missions and subsequent robotic explorers is the foundational knowledge upon which we will build our future as a multi-planetary species. But beyond its practical utility, the moon remains a philosophical touchstone. In its silent, cratered face, we see the reflection of our own world's violent infancy. It is a monument to the creative power of destruction, a testament to the fact that from the most unimaginable violence can emerge beauty, stability, and the potential for life and consciousness. This bond, forged in fire, is now a cornerstone of our cultural and spiritual heritage. For all of human history, the moon has been a constant in our sky, a silent companion to our own evolution. It has been a god, a goddess, a marker of time, a source of light in the darkness, and an inspiration for poets, artists, and lovers. Its phases have dictated the rhythms of agriculture and religious festivals. Its pull has been felt in the tides of our oceans and, some believe, in the tides of our own minds. The human impulse to reach for it was not merely a political or scientific ambition, it was the fulfillment of a deep-seated, ancient longing to touch the celestial companion that has watched over us since the beginning. The iconic photographs of Earthrise over the lunar horizon, taken by the Apollo astronauts, did more than document a mission. They fundamentally shifted human consciousness, giving us the first true glimpse of our world as a fragile, isolated, and breathtakingly beautiful oasis in the cosmic black. The moon gave us the perspective to see ourselves. And so, as the final notes of our story settle, we find ourselves at the heart of a beautiful paradox. The very event that should have been the ultimate cataclysm, a collision of almost unimaginable fury, became the author of our world's stability and the sculptor of its habitability. The void where Theia once orbited was filled by a new world, born from the ashes of the old, a world that would become the keeper of our history, the regulator of our climate, and the beacon in our night sky. The story of the Earth and the Moon is a single, unbroken narrative, a 4.5 billion year epic of gravitational embrace. It is a story that teaches us that chaos and order are not opposites, but partners in the dance of creation, and that the conditions for life are not a simple checklist, but a delicate, intricate, and hard-won tapestry woven across deep time. So, the next time you find yourself beneath a clear night sky and you see the moon hanging there, serene and silent, remember the colossal journey you are witnessing. You are not just looking at a rock in space. You are looking at a piece of your own world, a partner in a dance that began before a single cell divided, a guardian of our seasons and our spin, and the silent, enduring witness to the entire history of life on Earth. Its gentle, reflected light is the echo of the most violent day our planet has ever known, a perpetual reminder that from cataclysm can come calm, from destruction can come creation, and from a chaotic beginning can emerge a world of profound and peaceful beauty, capable of looking up at its own origins and feeling a sense of wonder. Let that feeling of deep time connection, of cosmic gratitude, lull you now into a state of perfect peace. The story is complete. The cradle, rocked by the hand of its own child, is steady. You can rest. Thank you for joining us on this slumber expedition to the very beginning. May the quiet, enduring presence of the moon guide you into a peaceful and restorative sleep. Good night.